There we go. I think it's because I wasn't capturing the entire screen, the desktop. All right. We have a lot to do today, and so much that I put a lot on a sheet for you to just kind of edit, because you sitting here copying down all my images would just take too long. So we ended class last time talking about trying to find the area underneath curves using an approximation of rectangles, right? And we are going to dive very deep into that today. And so we're going to start with a couple of problems. The first one being here, trying to estimate the area under a function using a couple of different methods. So we're looking at this first one here. We're going to look at the function x squared. Okay, everyone keep in mind the function is x squared. We're going to be looking at it on the interval 1 to 5, and we're going to be trying to estimate its area. And we're going to do it these 4 ways. The first way, we're going to just use 2 rectangles and use the right endpoints to form the height of our rectangles. Then we're going to do 4 rectangles. Then we're going to do 2 rectangles using the left end, and then 2 rectangles using the middle. And we're going to do all that by hand. And then when it's all done, we're going to come up with a formula for n rectangles. And then when that's done, we're going to let the number of rectangles go to infinity. And we're going to get the true area. And after all that's done, we're going to come up with the general formula for any function, not just this one. Any function on any closed interval, a formula to find the true area. Right? That's where we're going today. All right, let's get going. Whoa. So we're going to start with this picture here. And what I'm going to... Whoa, what did I just do? Oh, oops. Okay, what we're going to do to start with this, keep note that at the top, the computer already has computed the estimated area. So our answer should come out to be 68 here by getting the area of those rectangles. And when I do this, you're going to be sitting there going, why are you approaching it this way? Like, I can just look at that and get the area. The reason why I'm going to approach it the way I am is because we're trying to build up to a generalization, a general formula. All right? So you're just going to have to bear with it for a while, because it's going to feel like torture. Okay, does everyone agree that we have the interval? Let's see, 1, here's 5. We're looking at this function. We have 2 rectangles in there, right? I'll label them rectangle 1, rectangle 2. And I'm going to label a couple of other things here. I have this point here in the middle where the 2 rectangles change, right? Label that. That's 3. I'm going to give these numbers, 1, 3, and 5, and give them some other variables to indicate what they are. And we'll use those later. The first number in our interval I'm going to call A. The last number in the interval I'm going to call B. And the middle one, I'm going to label that one, but I'm going to kind of do it a different way. Go back to A. I'm also going to call that one X naught, X with a little 0. The second one, the 3, I'm going to call X1, and then X2. So we have, you can look at it as we have 3 X values. X0, X1, X2. They are 1, 3, and 5. Yes? But the endpoints, they get a special label, A and B. Now, what I can also kind of see as I'm looking at this is that the distance between, or you could say the base of my rectangles, they're the same, aren't they? That measurement is what here? 2, right? 2. The question becomes, what's the height of the rectangle? So I put in that little height there. I'm going to draw a little arrow because I'm kind of running out of room. The height of that, isn't that the function's value there? Right? So watch the way I'm going to write this. It's the function evaluated at what point? 3. But again, because we're building up to a generalization, I'm going to say x1. Do you agree? It's the function evaluated at x1, which in this particular problem, that point is 3. Any questions? You agree? Okay, now what's the height of the second rectangle? It's f of x2. which for us in this problem is f of 5. Can y'all read the small print like that? Is that all right? It's the first time I've ever used a pen that's that thin. Looks okay? All right. Okay, now, at this point, we're going to compute some things that will become normal for all of our computations. All right, what we're going to do is first, you'll always do this, you're going to take b, subtract a. What's b minus a for us? That's 5 minus 1, which is 4, right? So it's basically the end point of the interval minus the first point, right? The right end, left end. Now, isn't that kind of like the width of the interval, basically? Right? That's the width of the interval. Now what we're going to do is we're going to compute a number that represents the number of rectangles we would like to put in here. And in this problem, how many rectangles were there? 2. We're going to call this number n from now on. N is going to be our number of rectangles. And in this problem, it's 2. Now, what that allows us to do is if we know how wide the interval is, and we know how many rectangles we're supposed to put in that interval, then aren't we able to then compute how wide each rectangle should be? By doing what? Dividing, right? So if I take the b minus a, that's the width of the entire interval, and I divide it by the number of rectangles, that will give me, in this problem, what, 4 over 2? Which is 2. Yes? We are going to call this delta x. Delta representing change, right? That represents like the word change in x. So what we're saying is that when you look at a rectangle, you look at its base, it's delta x is how wide the base of each rectangle would be, right? Okay, now let's talk about the area, our estimated area. Do you agree that the area, now I need to somehow tell you this is going to be the estimated area, so I'm going to put a tilde over the a, just so we all agree, okay, that represents the estimate, okay? If I put capital A, you might think I mean the true area underneath there. So a tilde will represent our approximation. Won't it be the area, the exact area of rectangle 1 plus the area of rectangle 2? Right? So just notice how I'm using subscripting here, just trying to keep things organized. What is the area of rectangle 1? So this will be kind of separate work under here. The area of rectangle 1 is, you could say it's width times its height, right? Or you could say it's height times its width. It doesn't matter which order you go in. I'm going to go height times width, only because I know where we're headed with this, all right? So height times width is what I'm going to put down. So for us, what is it? What's the height of rectangle 1? Don't give me the number yet. Give me the general, even more general. It's f of x1 times, what's the width? It's, that's the width of the whole interval. Yes, it's x1 minus x0, but it's the common width of all the rectangles. And wasn't the common width of all the rectangles our delta x? That's right. Where did my delta x go? I don't know if I erased it. I was having that same issue last night. Okay, I'm going to just put delta x here. It's probably going to reappear here in a second. Does everyone agree that the area of rectangle 1, the area of rectangle 1 is its height, which is f of x1 times delta x, which is its width? That okay? No one has a question. But that is really just equal to f of, in this problem, only in this problem, f of 3 times delta x, but delta x is what? 2. Now what is f of 3? 9. Where are you getting 9 from? The function was given in the beginning of the problem, right? The function up here way at the top was x squared. So when I plug in 3 into this function, I should get 9 times 2, which is 18. So the area of that first rectangle is 18. Big deal. Like I said, we could have figured that out a long time ago. Now the next rectangle. Area of rectangle 2. It's f of x2. That's how tall it is, right? that's its height, times delta x again. In this particular problem, x2 is actually 5, and delta x is 2. Plugging 5 into the function, we get 25 times 2, which gives us 50. Right? Any questions on that? Add the 2 up, and that's your approximation, right? So our approximation should be 68. And if you go back up, remember I said the computer already did that for us, that should be our answer at the end. Okay? But that, like I said, it's not about the fact that we found the area was 68. It's the way that I'm starting to come up with this idea of how I'm going to create rectangles, how I'm going to label things. Because when you let n become infinite, how do you know what to plug in? You don't. You're no longer talking about specific values. So you have to have this formula that you can apply a limit to. That's where we're going. No questions? Okay, so now we're going to move on to the next one. For the next one, I'm going to do the same problem, but now I'm going to do 4 rectangles. Sorry, same function. Yep, same function. So what answer should we get here at the end? We should get 54. So here's the way I'm going to start. Again, I'm going to label the important points, which are our endpoints. The 1 and the 5, right? I'm going to call those A and then B. Since I'm doing 4 rectangles in there, it just works out perfect, doesn't it? That they land right on those integers, 2, 3, 4, which is great. But if I did 5 rectangles, it wouldn't, would it? Land right on perfect integers. So I'm trying to still kind of keep things nice at the moment. Now, let's label these x. The A is going to be our x0. Then the next one, x1, then x2, then x3, then x4. So we have 5 points on our x-axis. Let's find the width of the entire interval. That's b minus a. Has that changed? No, it's still 4. Let's find n, the number of rectangles. What's the number of rectangles I want here? 4. Let's find delta x. What's delta x in here? It's b minus a over n. So 4 over 4 is 1. Still follow? Okay. What would a tilde be? What's a tilde? What's our approximation? Each rectangle, right? A1, the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus area of rectangle 4. Now, I know some of you, I've heard you talking about, I've seen it in some of your work. You're familiar with summation notation. We're going to do that today. We're going to talk about it. I'm just not quite ready to go to it yet, all right? Or sigma notation, however you want to say it. Okay, let's find the areas of each of those. Oh, you know what we didn't do? We didn't find the heights. Let's talk about the heights. The height of this first rectangle, and I never labeled them, R1, R2, R3, R4. Okay, so the first rectangle, its height is f of x1, which in this problem is f of 2, right? What's the height of the second rectangle? F of x2, which again here is what? 3. And then f of x3, which is f of 4. And finally, f of x4, which is f of 5. Now, I want to point something out here in this problem that is going to be critical later. I want you to start seeing it now. Do you agree that x1 is actually a plus delta x? Okay, what is a? A is 1, isn't it? So you start out here, but then you add to a delta x. What's delta x? It's 1, right? So to get to x1, you actually start at A and you add 1 width of a rectangle, right? To get to x1? Yes.
I do have a question about the delta x. So the second step here, you're labeling the intervals, the x, 1, 2, 3.
I'm labeling the right ends of the end points of the base of the rectangles. Where the rectangles come down, I'm labeling all those points where they hit the x-axis. But in my height of the rectangle, I'm using the right side of the rectangle. That's why I'm using x1 and not x0, because I'm using the right side. So no questions on the a plus delta x? No? Okay, what about x2 then? Exactly. x2 is a plus 2 of the delta x's. So to get to x2, what I do is I start at a and then I add 2 jumps, right? 2 rectangle jumps will get me to the x2. See it? Okay, what about x3? A plus 3 delta x's. And finally, a plus 4 delta x's. That's going to be vital in just a little while, to see that each one of those points can be written as a plus however many jumps you are to get there. All right, let's get our areas of our rectangles here. What's the area of rectangle 1? F of x1, right? Times delta x. F of x1 is the same as f of 2 times delta x in this problem is 1. What's f of 2? 4. So 4 times 1 is 4. What's the area of rectangle 2? F of x2, delta x. x2 is 3 here, right? Times delta x, which was 1, so 3 squared is 9. I'm going to do the next 2 in silence. Seeing that whether or not you'd be getting the same thing I'm getting here. Yes.
So the rule is going to be x squared for all the questions.
Oh, today. On this, all I'm using x squared for is for this example to get us to think. Later on, we're going to generalize this for any function.
I just wanted to know where did you get the...
Yep. We'll continue to use x squared because the problem I had put up, remember at the beginning, where is it? Here it is. I said we're going to do these 4 things using x squared. Okay? And we are on part 2 of these 4 things. The gentleman that just came in, do you have a copy of these notes? Were they on your table? No? You might want to use this. It'll help. Oh, hey, what do those add up to be? 51? Or 54? It's 54, right? Yeah, okay. So they add up to be 54. That's our approximation, right? Any questions? Okay, we're going to move on now. And we're going to move on to, yes.
You like once you know the delta x, right?
Mm-hmm.
And you know you're gonna multiply with the heights. Can you just subtract it off and just add the heights? Together?
Sure. Yep, and we're going to wind up doing that. When we generalize, that's what we'll wind up doing. Yep. Okay, so take a look at this now. We're going to do the same thing, two rectangles. So we're back to two rectangles, but instead of forming our rectangles using the right endpoints, we're going to do the left. So can you see we still have the same interval here? We have A is 1, B is 5. We cut it into two rectangles. So we've got this important point here. You know, these 3 points here. But see, when we pick the height, we're not going to be going off the right endpoint. Do y'all see the difference between the right and the left? When we look at these heights now, let me illustrate. I can't even put the little bracket in there. The height of my function is going to come off that left side instead of this, instead of the right. Now, I haven't labeled them yet, okay? But that's the idea. It's going to come off the left side instead of the right. Now, we're going to call that first A. We're going to call it x0. Call this one x1. We'll call this one x2. Let's go back up and label those F's. Off that first rectangle, which I'll call rectangle 1, and rectangle 2. What's the F? F of what for rectangle 1? F of x0, which for us is F of 1. And then on the second rectangle, the height is what? x1, and then F of 3 in this. And there is no, we never get to the end, right? Because we always pick that one to the left. Yes?
You don't need to label the 2 and the 4.
No, because we only have two rectangles.
So only label the one that gives us the height.
I'm only labeling, see, if we have, remember the interval is what, 4 wide? We're going from 1 to 5. So our width of our interval is only 4. So we're going to go 2 rectangles, we cut it in half. And that's why I'm only picking up the middle number, the 3. Does that make sense? That might have been a little clearer when I did the next step, which was to get my B minus A, which was still 4. My number of rectangles was what? 2. And my delta x here would be 2. 4 divided by 2. So the width of each rectangle should be 2. So what's my A tilde here? R1. AR1, sorry. AR1 plus AR2. I think we can probably get these a little faster now since we've done these. What is the area of rectangle 1? It's the height, right? So it's F of, I'll say 1, delta x, which is 2, plus, what's the area of rectangle 2? F of 3, delta x is 2. So I'm doing it all in one line here. I'm just continuing. Area of rectangle 1 is that, which is that. What's F of 1? 1, so 1 times 2 is 2, plus F of 3 is 9, times 2 is 18. So our estimate is 20, and that matches with what the computer got for that. Oh, man. Questions? All right, for the last one, I'm going to go really quick through this one. Really quick. I'm actually going to start off by labeling A and B. Okay? I'm going to do B minus A right now, which is still 4. How many rectangles do I want? 2. So the width of each rectangle would be 2. So that's how I still get my 2 endpoints in my middle, right? The 3. I know that each rectangle is 2 wide. However, the point that I'm going to use to find the height is not the right end, it's not the left end, it's the middle point. So it's actually the point in the middle of the rectangle here, which I will call x1, x0 we could call the A, but what's more important is that we have 2 points here, x1, x2. Those are the ones really that we need in our formula. See, and we grab our height off of those instead. Do y'all see the difference between the left, right, and middle? So we get f of x1, which is here f of 2, f of x2, which for us is f of 4. A tilde would be area of rectangle 1 plus area of rectangle 2. What are those? Am I going too fast? The speed's okay? Area of rectangle 1 is f of 2 times delta x, which is 2, plus area of rectangle 2, which is f of 4 times delta x, which is 2. F of 2 is 4. 4 times 2 is 8. Plus f of 4 is 16 times 2 is 32. Our estimate is 40, and it matches. That's it. Questions or any comments? Okay, now let's get down to serious business. We have seen that using right, left, or midpoints gives different answers, right? And do you remember in last class I had an animation where I showed you like a bunch of rectangles using right, a bunch of rectangles using left, and a bunch of rectangles using middle? And I think we had said like the middle looked like the better. Well, it turns out that at the end of the day, it doesn't matter. You can do right, left, middle, any point in the interval. Is if you let n get large enough, it's going to converge to the real area. Okay? So that's what I say here. Different answers, but when n gets large, they will all get close to the true area. And I say C5-1-7. When I did that note in last lecture, I showed you that, what I'm talking about right now. So we now wish to create a general formula for n rectangles. And by choice, by my choice, I'm going to use right endpoints to create my formula. I could have used left, I could have used mid. I'm using right because I know that at the end, it doesn't matter which one I do. All right, before we begin that, you have to know some stuff about sigma notation. So this should be printed out, right? You have this? I don't have to. Okay. So first thing, this right here is the Greek capital S, right? Greek letter. We use it in mathematics to represent a sum. If we put k equals 1 on the bottom of that sum, that's called the start of the index. And then the top, the n, is called the end, E-N-D, the end of the index, or the stopping point of the index. Now don't confuse that n with the n that we had for number of rectangles. They're not the same thing right now. So what this does is it allows you in a very condensed, tight way to write something that represents the sum of a bunch of things. So if I write down, see, a sub k, that's the thing that I'm going to start adding up. The k here is the subscript. So the way the summation works is you start at 1, the starting point. So I write down a, replacing the k with 1, I get a sub 1. Then plus, now let the index go up by 1 to 2. Then, so I add to it a sub 2. And then the index goes up again to 3. And then the index keeps going and dot, dot, dot. You keep adding things up until you stop and you get to the n, whatever that n might be. So I have an example here in blue. If I say, find the sum from k equals 1 to 3 of this expression here. What you do is you first write that expression down, replacing the k with what? 1, which is right there. So it's 1 plus 2 times 1, and then all that squared. Then plus, now let your index jump up to 2. You rewrite the whole thing, replacing your k with 2. And then you keep going till your index ends, which I stop at 3, don't I? Then you have to compute all those and figure out what it is, and I did that, and it's 83. Okay? Here's another one. The sum from k equals 1 to 4 of k to the k. So I start at 1, I write 1 to the 1, plus 2 to the 2, right? Then 3 to the 3, then 4 to the 4, and that's where I stop. And I didn't even figure out what that was. So the k is the thing that changes, right? The k is the thing that changes. This k, some of you may have taken another class that you did sigma notation. The common letters that we use for our index are k, j, and I. So you may have seen this all done with i's instead of k's. I like to use k's. It's just my preference. What else do I want to say about that? You can add forever to infinity. So you can have a summation that starts at 1 and goes forever. And that's what we will study in chapter 8. These are called series. So we'll study that. We're just not there yet. Any questions on that? Yes. It will always start wherever it says it starts. You don't have to start at 1. You could start at 0. You could start at 2. Your index can start at any non-negative integer. So 0, 1, 2, 3. And it stops at any integer greater than your starting or equal to it. And it always jumps up by 1. There's another type of, not summation, but there's another type of thing like this. I don't know if you've ever seen this. Does anyone know what that is? That's a capital pi. So that's capital S, Greek, right? That's capital pi. That's the same as sigma notation, but instead of adding, what do you think it is? Multiplication. Sigma is for S. S is for sum, right? P is pi, right? Is for product. And so that's a product. So if you wanted to multiply things n times, you could use that instead. That's just FYI. We're actually never going to touch that in this class. What else? Okay, I think that's it for that. But there are some other things we need to look at in terms of these formulas. There are some common sums, and you need to know that these exist. I wouldn't necessarily say you need to memorize them, but you need to know they exist. You need to know that I gave you a handout that had that formula on them. Okay? I've really been known in Calculus 2 classes to allow you to use like a reference sheet or something on a test. So this might be something you would jot down on that. We'll just have to wait until we get to our first test. So this first one, the sum k equals 1 to n of k. So that means you start with k equals 1, then you add to it 2, then add to it 3. So this is just adding up integers, isn't it? What's 1 plus 2 plus 3 plus 4 plus 5 out to, let's say, what does my example go to? 200? So if you take 1 plus 2 and you keep adding those numbers up all the way out to 200, the answer is very simple to find. It's just that last number you're adding. Okay, it's that last number, n, times that number plus 1 divided by 2. And it will always be that way. And I'm not here to show you why. I will, if you come into my office, I'll show you why that's true. But for this class, we don't have time for it. So that means if I say, what's 1 plus 2 all the way to 10, what would it be? 10 times 11 over 2. Okay, 55? All right, now that's the sum of the first n consecutive integers. The second common formula that everyone should know, or be aware of that exists, is the sum of the squares. So what's 1 squared plus 2 squared plus 3 squared all the way out to n squared? Well, it's n times n plus 1 times 2n plus 1 all divided by 6. And again, I'm not here to show you why. That's just it. And then there's one last one that we should know, and it's the cubes. You might want to go do some jumping jacks. You do something out in the hallway or something, all right? Unless you can tell me right now what one cube plus 2 cubed all the way out to 100 is. No? Okay. Sum properties. So we're almost done with the sums here. Here are some things we're going to need. Anytime you have a sum and you're trying to add up a bunch of things. So the a sub k is the thing that keeps changing every time. But if you have a constant sitting in front of it, a number, that c is a constant, that you are allowed to just peel that constant out in front of the sum. Just take it out, like a factoring. So we need that. This is an example of it. I'm trying to add up 3k squared. The 3 is a constant. I pull it out in front. And then the k squared, I have a formula for, right? So I just throw the 3 in front of that formula, and I'm done. You should also be aware that whenever you have a sum and you have two things being added, and each one of them are changing. So they're not the same. Each one is different. What you can do is you can break it into two sums and add them up separately. So I did an example of that below. Last one. This is kind of an interesting one. What is the sum of a constant? See, because what's changing? Every time you change the index, it goes 1, then 2, then 3, right? But that only changes for the k in the problem. If I write down a number, a constant, like look at this one right here, 3. You're supposed to start at k equals 1, but there is no k in there, right? It's just 3. So what happened? It's 3 plus 3 plus 3 plus 3 n times. So I kind of illustrated it here. What I did is I said, look, let's say you have a constant here. What you do is you use that property I just showed you that the constant can come out, which leaves you with the 1. And so if you sum k equals 1 to n of 1, that means you're going to have n ones added up together. And then what you do is you come back through with that constant, multiply it, and it's just c times n. So look at this. What's the sum? K equals 1 to 97 of 3. 3 times 97. Okay? That just remember that. That's what whenever you have just a number by itself, it's whatever that number is times whatever the index is. Stops at.
What if K was like 3?
That wouldn't be true. Because you wouldn't have those first few terms.
Okay, I start at 1.
Yeah, for this to work, for that formula to work, k has to start at 1. Yeah. Now, how about this one? See if I can trip you up on this. Just 3?
Yeah.
How is it just 3?
3 was constant, right? So, plug out.
You can pull a 3 out,
Yeah.
and that's 1 over n.
And then n over n is 1.
N here, isn't n a constant? I mean, n is a number, isn't it? Like in this problem I just did with the 97, oh wow, oops. With the 97, that 3 right there, I could have said 97, couldn't I? And then it would have been 97 times 97. N here is still not affected by k, is it? K is the thing that changes. So if you don't have k in your formula, any other letter that's there is a constant. So I could have really pulled not only the 3 out, I could have pulled the 3 over n out completely and left a 1 there.
But it goes up to n.
But it goes up to n. So that adds up to be, what, 1 times n?
Yes.
Which is n, which turns out to be 3. So yes, people said 3, yes. Yes. What was your? Yep, that's how it'll turn out. So this right here adds up to be n.
So the variable is going to be always k.
whatever the index is the only thing that's affected by the sum. So if it's j's or i's, if that's in your formula, then you have to leave it. If you have this sum, I'll do that same problem. K equals 1 to n. Instead of 3 over n, how about 3k over n? Pull your 3n out. Sum k equals 1 to n of k, right? K is the only thing left. What's the sum of the first n integers? N times n plus 1 over 2. Right? So that, does everyone understand that right there? This is one of the common formulas I just gave you. Right? So it turns into this. And then now the n's cancel. So you're left with, I'll put it up here at the top here. Well, 3n plus 1 over 2. Or 3n plus 3. Doesn't matter. Just leave it like that. That okay? That's what we need. Here we go. We are now going to take this problem. The function is still f of x equals x squared. We're still on the interval 1, 5. But we are now going to try and do this with n rectangles. All right? N rectangles. So do you see in the graph I kind of left the middle like I erased it? I did that because I don't want you to think that there were actually 1, 2, 3, 4, 5, 6 rectangles here. There aren't 6. There's n of them. So right now, you can't tell me right now where these things hit the x-axis. Like you can't say, oh, that's hitting at 3, or oh, that hits at 2, because it's n rectangles. Right? But we're going to start with the same systematic approach that we did earlier. I'm going to label A and B. We still know B minus A is going to be 4, right? The next thing we normally looked at was n, right? N was the number of rectangles. So what is n for us here? Not yet. We're not going infinite yet. We're doing n rectangles. So n is n. Okay? N is n. We're not going to fix it to a number. It's an arbitrary value, integer. What is delta x? B minus A over n, right? So the width of each rectangle should be 4 divided by n. That makes sense, doesn't it? If we have one rectangle, how wide is it? 4. If we have 2 rectangles, how wide is it? Each one is 2, right? If we have 3 rectangles, how wide is each rectangle? 4/3, right? If we have 4 rectangles, they're each 1 wide. If we have 1,000,000 rectangles, they're each 4 1/millionths wide. But that's a generalization of it, isn't it? That's what we're trying for here. Now let's label some points. The first point here we will call x naught, and that's A, isn't it? Now, our next one is x1. But how did we say we could get to x1? By taking A and adding to it delta x. Agreed?
Is x1 just arbitrary along the...
Yeah, we don't know where it lands. What we do know is that it's wherever we started plus whatever the width of a rectangle is, right? Any questions on that? That's critical that you see that. But I can go even further than that, can't I? Can't I say that that's A plus, what's delta x? 4 over n. And I'm going to even stress it a little bit more. I'm going to put a 1 right in front of that 4 over n. Because what that's saying is, I need to get up just to get up and stretch my legs. What I'm saying is that to get to the x1, you start at x naught, or you start at A, right? And you jump 1 width of a rectangle, 1. The next one, we're going to do what? We're going to do, to get to x2, which would be my next right endpoint, I would take A and jump, how much? 2 of the delta x's, which is really It's a plus 2 of my delta x's, which is a plus 2 times 4 over n. And yes, I understand that you could make that 8 over n. Don't, because of where we're going with this. All right, what would the next one be? X sub 3. A plus 3 delta x, which is really a plus 3 of these 4 over n's. And I could keep going, couldn't I? And going and going and going. And what I would do is I would get to the final end of this. And what would that be? X what? X sub
A plus n delta x.
oh, I'm trying to figure out why is my toolbar up here? What's that? Oh, there it is. Thank you. Thank you. So which one is this one? This would be x sub n. It is the nth right endpoint, isn't it? And that would now turn into a plus n delta x's, which is really a plus n 4 over n's, which is a plus 4. And what's a? What's a? 1. And what's 1 plus 4? 5. So it should be 5, right? But I'm still going to leave it as a plus n times 4 over n. Yeah? Okay.
Why is it x1? See how you're going x1
That's x1 represent, so when we say x sub 1, it represents the, x sub 1 is the x coordinate of the right endpoint of the first rectangle. X sub 2 is the x coordinate of the right end of the second rectangle. When I get all the way out to the last rectangle, I'm at the nth rectangle. Right? I'm at the nth, because there are n rectangles, there's not 5 rectangles, there's n of them. Right? Everyone else okay with that? Pardon me? Oh, I forgot to change it over. Yeah, you're right. It is taken from the midpoint. I didn't realize that in my picture. Good call. That picture should be, these should be like this. You might want to fix that because it doesn't correspond with the right endpoint. I got too gung-ho last night trying to put this together. Forgot to switch off. Okay. Any questions before we proceed? What part? Well, because look at my pictures. My first rectangle is supposed to go off of the right endpoint, go up to the function and go over. But it's actually going off the middle. My picture's wrong. Nothing's going to change for us. I mean, it won't matter when we let n go to infinity, right? But in terms of our heights of our rectangles, because the next thing I'm going to ask for is how tall is this rectangle here, right?
This would be the same way to set up any of these.
You could do it, all of them like this, yeah. So how tall does this one, how tall is this rectangle? It's f of x1, right? Which is f of a plus 1 times 4 over n. Do y'all see that? All I'm doing is I'm picking off these guys right here, off the bottom. What would the height of the next rectangle be? And I'm just going to go straight to it. F of a plus 2 times 4 over n. The next one would be f of a plus 3 times 4 over n. And keep on going till you get to the very last rectangle, And the height of that rectangle would be f of a plus n times 4 over n, and that's it. All right, I'm ready to proceed. Can I scroll down? Anyone need this? All right, then let's talk about a tilde. Let's talk about our approximation. Isn't it area of rectangle 1 plus area of rectangle 2 plus all the way out until I get to area of rectangle n? Isn't that, though, just, well, I want to, but not yet. Area of rectangle 1 is f of a plus 1 times 4 over n times delta x. What was delta x for us in this problem? 4 over n, so times 4 over n. Okay, that's my first rectangle, right? Everyone see that as being my first rectangle? What's the second rectangle? F of a plus 2 times 4 over n times 4 over n again. And I keep doing that, don't I? Until, maybe I'll do one more. I think I will do one more. The next one would be f of a plus, what? 3 times 4 over n. All of that times 4 over n. Now plus dot dot. What would the last rectangle be? I'm going to run out of room. I'm going to just go down a little bit here. F of a plus n times 4 over n times 4 over n. All right. Would you agree that that sum, the only thing changing in each of those sums is that 1, 2, 3, 4, all the way out to n? Everything I've done in blue, right? It's the only thing that changes each time, and each of them goes up by 1 each time. 1, then 2, then 3, then 4. Isn't that perfect for summation notation? Okay, so let me try that. I can rewrite this then as a sum from k equals 1 to n of f of a plus what? K times 4 over n times 4 over n. That would add up the areas of each of the rectangles. Yes?
So, for instance, this one, A is a constant, right?
A is a constant. I'm almost there. I wanted to keep the A there as far as I could until we're ready to plug it in. Because remember, the next thing we're going to do after this is we're going to come up with a general formula for any function, not just x squared. And not just between 1 and 5, between A and B. So, what's that? Okay, any questions on this? I have to go to a new page, so I'm going to flip to a new page here. We are at this sum k. Okay, what the heck happened there? K equals f of a plus, it was our k, and then our 4 over n, and then, hey, how about this? Why don't I pull the 4 over n out? Can I pull that 4 over n that was in the back out?
Yeah.
Yeah, sure, because 4 over n, that is a constant. Why is it doing this? 4 over n is a constant, so I pulled it out. Now, we need to be very careful. F of a plus k times 4 over n That right there, we can't do anything to unless we know f, right? We have to know what the function is to be able to do anything here. We know what that function is. It's x squared. So if I say, hey, take this and plug it in the function, I'm saying take that and square it, right? So I'm ready now at this point to get rid of the f and plug that stuff in to the function. So I'm going, when you plug it in, you get a plus k times 4 over n. So this is the first time I actually put that k up there with that 4, okay? I just slid that k up with the 4 over n. And now I need to say squared. That's the key. Look, we've lost the function by actually plugging that thing into the function, which is the squaring function. Had it been x cubed, we would say x cubed, right? Had it been e to the x was our original function, we would have what there? E to that. Any function we have, that's what would have been plugged into it. All right, can we square that, everyone? All right, it's 4 over n sum k equals 1 to n. Square it, we get a squared plus 8 a k over n plus 16 k squared over n squared. So I hope everyone understands what happened there. This thing times itself, right? FOIL out. Right, a plus 4k over n times a plus 4k over n, FOIL, collect like terms. So star that. If you don't know what happened, you can figure that out later, but that's what it turns out to be. Now at this point, I think I'm ready to get rid of my a's, because a in our problem was what? It was a constant. It was 1, wasn't it? So I'm now ready to eliminate my a's. Bless you. I have 4 over n sum k equals 1 to n, 1 plus 8k over n plus 16k squared over n squared. Questions? Now we had a property a little while ago that said that if we have a sum and there's things that are being added up together, we could break it into separate sums. That's what I'm going to do now. I'm going to take my 4n, leave it 4 over n, leave it on the outside. Then I'm going to do sum k equals 1 to n of 1 plus sum k equals 1 to n of 8k over n plus sum k equals 1 to n of 16k squared over n squared. So just split it into 3 sums. Your hand might begin to hurt a little bit if you're not used to writing this sort of stuff over and over and over. Can anybody tell me what that first sum is? Not the 4 over n, leave the 4 over n out. That first one, sum k equals 1 to n of 1. It's just n. That was that property where you just, all you had to do, if you have a constant here, is multiply 1 times n, right? Now on the second sum, take out the constant. What's the constant in that problem? The 8 and the n on the bottom, right? And you're left with sum k equals 1 to n of k. And that, yes, is one of our special sums, isn't it? That's right. I'll do that next line. Next one, I'm going to pull out, what can I pull out? 16 over n squared, then I'm sum k equals 1 to n of k squared. And that, again, is also one of my special sums. N times n plus 1 times 2n plus 1 over 6. You know, that's what it is. Can we shut the door? Because I think it's classes are changing out right now and it's probably going to get loud out there. Thank you. Do I have any questions up to that point? We're getting pretty damn close to the end here. 4 over n times 8 over, or plus 8 over n. Now that red box turns into n times n plus 1 over 2 by the formula I gave you, plus 16 over n squared times that box turns into n times n plus 1, 2n plus 1, all over 6. We actually get some cancellation to happen here.
Yes. The 8 and the 4.
Those ends are gone. That 2, that 4,
And the square.
this 8, and that becomes a 3, that n, and then one of those. So things start to cancel and clean up, don't they?
Yeah.
See, I have n plus, what is this? 4, n plus 1. Was that the only thing left there? Yeah. Then 8, n plus 1, 2n plus 1, all over 3n. Y'all see what I'm doing? This is just some algebraic cleaning up. Is that all right? One last thing. Let's distribute that 4 over n through. 4 plus 16 n plus 1 over n, so 16 n plus 1 over n, and then plus 32 n plus 1 over 2n plus 1 over 3 n squared. And I will box this as our answer.
We post this, right?
Yeah, I'll post all this. Okay. What the hell does that boxed answer represent?
The area.
Of?
The end of one part.
Okay.
And square.
It's the area of n rectangles using right endpoints, right? That's the area of n rectangles. Now, in the very beginning of this class, didn't we do this and we did 2 rectangles using right endpoints? 2 rectangles. What was our answer on the very first example that we did? 68. We should be able to plug 2 into this right now, and it should spit out 68. Let's just check. Let's just plug 2 in real quick. If I plug 2 in right here, I get a 3. Here I get, what, a 2. Here I get a 3. Here I get 5. Here I get 2 squared is 4. So let's see. I have 4 plus 16. 8 times 3 is 24 plus, let's see here, 12, 15. What is it? What is this? 40? Oh, you're talking about the second one.
That's 48 over
Is that 68? So it matches, right? It better. Right? It better. So you may be saying to yourself, why all of this torture, right? Why torture yourself with all of this, coming up with this formula and all this crap, if we did it earlier pretty easily? And the answer, hopefully you have it on the tip of your tongue, is the fact that now to get the true area, we're going to do what? Take a limit and let what do what? Let n go to infinity. That's what we're about to do. Okay? So now using this answer right here, I'm now going to say, this is the area with n rectangles. Let there be infinite rectangles. And that's the next step. So in the next step, let me see if I put a slide here for it. I might have. Nope, I didn't. So I'll start out. So now, to get the true area, we let n go to infinity on the formula we just found. So I'm going to write down limit as n goes to infinity of 4 plus, someone's going to have to help me here, 16 times n plus 1 over n plus 32 2n plus 1 over 3n squared. So let's discuss here a little bit about what happens if n goes to infinity with the 4. Nothing, right? N doesn't do anything to 4, it's just 4. But in the second term, n plus 1, that goes to infinity, right? Divided by another thing that goes to infinity. So you have infinity, infinity, over infinity, which is perfectly suited for what? L'Hopital's rule. And then over here, we have an n plus 1, that's infinity. 2n plus 1 goes to infinity. 3n squared goes to infinity. So you have infinity over infinity again, which is perfectly suited for L'Hopital's rule. L'Hopital, though, you need derivative top and bottom, don't you? So before I apply L'Hopital's rule, what I'm going to do is I'm going to multiply some things through here, distribute my 16 through. I'm going to, not equals. I'm going to actually multiply n plus 1 times 2n plus 1, and then distribute a 32 through it. And I'm just going to tell you what it is. You could do it on your own time. And now I'm ready for L'Hopital. Some of you may have noticed that I use an L in a lot of textbooks, and other teachers use an H for L'Hopital. Personal preference. If you put H, I'm not going to count it wrong. But you always need to let me know if you're ever going to use L'Hopital's rule. You need to indicate it somehow. So I'm now going to apply L'Hopital's rule to this. So I still have limit n goes to infinity. 4 plus, okay, what is 16n plus 16? What's the derivative of the top? 16. Derivative of the bottom? 1, right? Okay, plus, now what's the derivative of the second fraction, the top? 128n plus 96 over 6n. Now don't you have, you still have infinity over infinity on this one, right? So you apply L'Hopital one more time. So one more application of L'Hopital. Limit n goes to infinity. You get 4 plus 16 plus 128 over 6. And that's a constant. In fact, if I clean this up, this is 20 plus 128 over 6. Now, I'm going to get the exact answer. The exact answer means I'm not going to pull out a calculator. What I'm going to do is get a common denominator and put these together. So 6, it's 120 over 6 plus 128 over 6, which is 248 over 6. That reduces, doesn't it? I could divide that by 2. 124 over 3. That is the exact area under the curve x squared between 1 and 5. 60 what?
41.
Now, this is the exact answer, right? Now, let's get the approximate answer. The approximate answer is where you break your calculator out and you do it. 41.333. It repeats forever, but that would be our approximate answer.
But it's different from the original one, 368.
Oh yeah, but we let n go to infinity. So go back to the first page we had. What? Look, here was the very first problem we did. Right? This is the very first problem we did. We had two rectangles in there. When we did it, we said, hey, the area is about 68. And that sucked real bad, because what does it say here the actual area is? 41.333. In order for us to get 41.333, what we had to do was come up with a general formula for n rectangles and then let n go to infinity. And that's how we were able to recover the area. I don't know if that answers whatever question. That's very painful, isn't it? It's a lot in there. But here's the importance. This is the reason why I cover this in a lot of detail, is because this whole concept of coming up with formulas and generalizing and all this stuff, I think that's really what will make you successful in Calculus 2 and even as an engineer. There's too many things out there that are just like, show me an example so I can just reproduce that. You're not going to be a good engineer if that's the way you look at everything. So, like the problem I gave you as a take-home quiz. You know, I didn't give you a template for that. I didn't give you anything in the notes. The only thing that would have helped you in the notes was the AB sine theta, 1/2 AB sine theta. That's probably the only real useful thing I gave you. And everything else was just what could you extrapolate from it. So this extrapolation of this formula and this finally getting to the 41.33, I think serves us as we progress in this course. As far as like, there's nothing out of bounds as far as what we're willing to try and attempt to get something to work. What time is it? 2:23. Now, half of you already know this, what I'm about to show you. And that's for those of you who talked about this in Cal 1, at the end of Cal 1, antiderivatives. Some of you may have seen this already. That if you take the function we were just looking at, right, was f of x equals x squared. If you can find its antiderivative, what is the antiderivative of x squared? It's 1/3 x cubed, or x cubed over 3. Plus some constant. Okay, now if you don't know what the hell I'm talking about, don't worry, we're going to talk about antiderivatives. But you should, even as a Cal 1 student, realize that in yellow there, if you take the derivative of that, you get x squared, right? Now check this out. What were the endpoints that we were looking at? 1 and 5? I'd like for you to first take 5 and plug it in here. What would you get? What's 5 cubed? It's 125, right? Divided by 3. So you get 125 divided by 3. Now what I'd like for you to do is plug 1 into this. And what do you get? 1/3? What I'd like for you to do now is subtract the 2. And what do you get? 124 over 3, which is the answer we just got. Right? So, but hold on. To get less than that, right? To get from here to here, to prove that that always works, is called the fundamental theorem of calculus. Okay? The fundamental theorem of calculus is the relationship between these two things. Before the fundamental theorem of calculus, before Newton was able to come up with this, people were just abusing themselves with this summations, trying to figure out these sums, and it was just crazy. Riemann was the guy who came up with this idea of these sums, the Riemann sums. That's what we call them when you cut it up into rectangles. So you're probably all, you might be upset with me about why you show me all this when it's just going to turn out to be this. I'm telling you, there's really a purpose for it. Because everything we do in Cal 2 where we have to take something and cut it up and add them up, if you don't have the idea of of how we did it here with rectangles, it's going to be very difficult for you to come up with formulas later. Because you never have that in your head of, oh yeah, we cut things up and we added up, it was width times height, and that's where we came up with these different components of the formula. You're going to be given a problem and you're going to have to create the formula. So you're going to have to understand how you're going to cut it up to make it happen. We're getting the carriage in front of the horse here. Let me get back to the end of today's lecture, which I'm going to try and do in 15 minutes. Let's try and do this in a general setting. Let me take a function. Let me just take any function. I'm not going to say it's x squared, so I'm just going to call it f. I'm going to take it on the interval a, b, and I'm going to try and figure out what the area underneath this is. And the way I'm going to do it is I'm going to cut up this interval into n rectangles, and then I'm going to let n go to infinity, just like we did before. Okay? Let's see how things would change by me not giving you the function and me not telling you what a and b are. Not a whole lot will change, as we're about to see. What is b minus a? Whatever the hell b minus a is. I don't know. How many rectangles do we have? N. So n is n, right? What's delta x? We don't know it. It's b minus a over n, whatever that is, right? What we do know, though, is that my first point, a, is my x0, right? And my next point, x1, will be that right side of the rectangle that I'm going to draw, right? And that x1, I will always be able to get to it by what? Taking a plus delta x. But for me, that's a plus b minus a over n. Isn't it? Delta x is b minus a over n. Now, what will the next one be? x2. A plus 2 delta x, which is a plus 2 times b minus a over n. Do y'all see how this is very naturally flowing from what we just did? And then I keep doing that until I get to the very end, to my nth x there, my x sub n, and that will be a plus n times b minus a over n. And you can kind of see from that the n's would cancel, right? And you would just get a plus b minus a, which is b. So you would be at the end. Let's talk about heights of rectangles. It's just f evaluated at each of these, right? That's what it would be, each of the heights. And then the areas, we'd add them up. And because we just did this, it's perfect for a sum, isn't it? So it would look like this. It'd be a sum. K would equal 1 to n. It would be whatever my function is at a plus k times b minus a over n. That's the b minus a over n is kind of like the 4 over n just was, right? And then over here times the width of each of the rectangles, which used to be 4 over n, but now it's b minus a over n. Is that it? I mean, this is my height, right? And this is my width. And I'm adding them all up. It is a constant. I can pull it out. I'm not going to, but I could, right? That adds up the n rectangles, right? But what do I want to do at the very end of adding them all up? Let n go to infinity. So what I do now is I throw in front of this the limit as n goes to infinity of this. This, my friends, is the limit definition for the area under a curve, right there. It's the limit of that. Any function. Now, what saved us in the last problem was that what did we do when we wanted to get rid of f? We took it and we squared it, right? But we couldn't go any further right now. We would be stuck right now. We'd stop right here until someone gave us a function. So all you have to do right now is give me a function in an interval, and I can plug everything into this, and I'm ready to go. I'll show you an example if you want to see it. You want to see how would I find the area under the function e to x on the interval, we'll make it real easy, 0, 1. How would I find that area? I would take the limit, n goes to infinity, of the sum k equals 1 to n of the function e, but replacing the x in the function with a plus all that crap, right? All this. But a is what for us in this problem? 1 plus k times, what's b minus a in this problem? 1, because it's 1 minus 0, over n. And then over here times b minus a, 1 over n. Pardon me? Oh, a is 0. Thank you. Gosh, I'm glad you pointed that out. A is 0. Don't know why I think because 1 from the last problem. 0. So you don't need that 0 in there. Does everyone see that? I messed that up. That 0 doesn't need to be there. It could just be e to the k over n. Now that limit we don't have a formula for. We know how to add up like k, right? The sum of k, it's n times n plus 1 over 2. Sum of k squared is this. We don't have a formula for e to the k over n. So we would be stuck. But that's the setup for it. Yes? Yeah, as long as it turns out to be in the form. But see, this wouldn't be. What would we get here? Let me actually write it out. It's, see, we don't have a sum. We don't know what those add up to be. If you go back to the previous problem, we knew what they added up to be. Where was it? Right here. The boxed red part, right here. We summed the k's, and that turned into a formula that no longer had a sum in it. When we sum the e's, you have to add them before you let n go to infinity. So you can't take a limit until you've added everything. See, here we could take a limit because the sum vanished, right? From here to here, that sum vanished because of the formula. For this problem, we couldn't do anything. We'd be stuck. But what I could ask you on a quiz is, give me the formula for the area underneath that curve. And what I'd want is this. In red here on the bottom, without the 0. Get that 0 out of there. Okay? I gave that as a quiz question last semester, and people didn't know what to do with it. I mean, after I went through this whole thing, and they didn't know what to do with it. So, does anyone have a question on that? Yeah, exactly. This is the area. This is the area. Yeah, it's a limit definition of the area under f on the interval AB. It's the true area. Yeah, it's using Riemann sums. I believe the book references this formula. Well, I'm not going to look it up. It's in there somewhere. Something like it. Sometimes I do slight variations to what the author does. Yeah. Okay. What do y'all think? Is it already almost time? Here's the deal. You're going to have a homework assignment, but I don't have it yet because I didn't know how far we were going to get with this today. So what I will do is I will send you an email within the next hour probably, and that email will contain what homework you have. I can already tell you that it's going to be things like estimate the area underneath this graph using 4 rectangles using right endpoints. And so you're going to have to do just like I did in the beginning. And then you're going to have one where you have to actually find the sum using all this crap that we just did. Yes? Problem, it's going to be, yeah, I think that's going to be in the homework. Don't do that. Just Wait for my homework assignment tonight. That'll be our first official homework assignment out of the book.
That does in the next 5 minutes to get time to
Next class, it was due at the beginning of this class. Yeah. Well, it's only because you could have sat there and worked on it, and you know, I'm just saying. I called for it though. Why didn't you turn it in?
Because I'm not right yet. I was
Oh.
work on it in the next 5 minutes. And turn it
Oh,
in.
beginning of class only. Sorry.